So today is our first session of digital electronics. Okay. So first confirm that am I audible properly? Am I audible? And is my screen sharing okay? Yeah. So then it's okay. So today is our first session and we are going to see what? We are going to see your digital electronics. So digital electronics, as you all are familiar, it is a very important topic for EC students in your gate as well as in PSUs, because in PSUs there are lot of questions that have been asked previously from digital circuits, and those questions, they are very simple, and the questions are asked from very basic, either they are asked from very basic circuits or they are asked from the first chapter. So let me first discuss with you the syllabus and the important topics that are there in your HAL or any PSU exams. Okay. So the first topic is what? It is your number system. Okay, number system. So this is very important, and usually questions are asked in PSU from this chapter, because these questions, they are, first of all, they are very easy to solve, and second, you can solve these questions very quickly. Okay, so in PSU, like in HAL exam, there are very less time. Okay, for solving each question there is very less time. So usually such kind of questions which are asked from number system, it can be solved within like 30 seconds. Okay, so number system. Second is what? Boolean algebra, or even logic gate can come. Boolean algebra. And the third is what? It is your logic gates. So these three are very important topics. Fourth comes combinational circuit. Fifth is sequential circuit. So this is very important topic. Sequential circuit. Okay. Next is your logic family. Now from this you can expect questions like put the formula, get the result, because there are lot number of formulas in this logic family, like fan in, fan out. Okay, so there are very much questions that are asked directly from your formula. Okay, so you can expect formula based questions from here. And seventh is memory configuration. Even this chapter there are formulas, but I don't think it will be that much significant in your HAL or PSU's exam. And last is ADC and DAC. So even in this chapter, I feel the questions, if it is asked, it will be put the formula and get the result. Okay, put formula and get result. Okay, like your resolution, and what will be means they will give you some voltage and they will ask you what is the binary equivalent of that voltage. When you have the resolution will be given. So all those kind of questions it will be given. Okay, so first let me know, in which topic you people face the most problem while solving questions out of these 8 topics. In which area you feel difficulty? First let me know that. In the first session I want to know where you people feel difficulty. Yeah, so anyone want to say where do we feel difficulty? Okay, so you people don't feel difficulty. That's very good, actually very good to know. Okay, so then first let us start with counters, sir. Counters. Okay, so in sequentials, okay, fine. So I know in counters most of you people might not that much comfortable. Okay, but in this starting topic like number system, Boolean algebra, logic gates, all of you are very much comfortable. Okay, So, okay, before starting this, first let me ask you, how many of you can represent this number 21 and minus 21 in 1's complement and 2's complement? Let me know very quickly what will be the 20 means what is the 1's complement representation of 21 and 2's complement representation of 21 and that of minus 21. First, let me know how many of you can solve this. Then I will do it. Okay. How many of you can solve this? See, what is 21? It's very simple. 21 is 1 0 1 0 1. 16 plus 4 plus 1. So this is 16, this is 4, this is 1. So that is 21. So this is what? This is your binary equivalent. Okay. Binary equivalent of 21. Now, there are few things. Okay. Like, how can you differentiate a positive number and a negative number in binary? So that we need to study. So anyone, have you got the answer for this one? 21 minus 21 in 1's complement in 2's complement? Nobody got? Okay. So then let us start the discussion now. So any kind of digital circuit, so especially in our digital circuits, we use a special kind of number system. That is what? That is your binary number system. Okay. Binary. What happened? Yeah, binary number system. Now the speciality of binary number system, it is that we have only two characters over here for representing. That is what? That is 0 and 1. Now if we use positive logic, so with positive logic, what happens? That 0 corresponds to low, or you can say even 0 volt, and 1 corresponds to high or plus 5 volt. Now with negative logic, there is one more kind of logic, that is negative logic. In negative logic, 0 corresponds to high, that is 0 volt, and 1 corresponds to low, that is your minus 5 volt. Okay, minus 5 volt. So this is your negative logic. Now, how do we represent numbers in your digital circuit? That we are going to see. So how do we differentiate a positive number from negative number? So there are various ways in which we can classify them. So the two most important that we use, that we have to study, that is sign magnitude form and complement form. Now the complement form, it can be subclassified into two more parts, that is 1's complement and 2's complement. So what is this sign magnitude form? So in sign magnitude form, suppose if I want to represent 21, okay, I want to represent 21. So here it is what? By default, if nothing is given, so this will be plus 21. So first, what is the binary equivalent of 21? We have just now seen that it is 101. Now if it is plus 21, so we are going to write it as 0 1 0 1 0 1. Now this 0, what is this 0? This 0 corresponds to your sign bit, okay, and this all other bits, these are your magnitude bit, okay, magnitude bit. Now if I wanted to represent minus 21, so then this will be represented as 1 1 sorry 0 1 0 1. Now this one is again your sign bit, okay, and this is your magnitude bit. So always remember, in your sign magnitude form or even in complement form, 0 will correspond to a positive number and 1, it will correspond to your negative number, and the leftmost bit in sign magnitude form or even in complements form, it is going to represent what? It is going to represent the sign bit. Okay, any doubts in that? Any doubts you guys have? Oh, so people are waiting in the lobby. Yeah. So sorry guys, I couldn't see you. Means you guys were waiting in the lobby. Yeah. So any doubts up to this point? Hopefully there is no doubt. If you guys have any doubt, you can just do what? You can type in the chat box and I will get back to you. Okay. Okay, fine. So now let us see how do we represent 21 in 1's complement and in 2's complement. Okay. So this is 21. If I want to represent, first I am showing you the representation of plus 21. So I am just brushing your concept once again. I know some of you might know this, but some of you might have forgotten this. So that is why I am showing. So in 1's complement or in 2's complement, so sign magnitude representation of positive number, it is equivalent to 1's complement for the positive number and it is equivalent to 2's complement for your positive number. So 21 plus 21 in sign magnitude representation, we just now saw it is 0, 1, 0, 1. In 1's complement, this will be 0, 1, 0, 1, 0. And in 2's complement also, this will be 0, 1, 0, 1, 0. Now, look very carefully. In your 1's complement, how do we represent? Minus 21. Okay, minus 21. So now look very carefully. In 1's complement, simply what we do, this sign bit, okay, this sign bit, it will now become what? It will become 1. And all other bits, that like you can see in the this sign magnitude representation for plus 21, bit by bit you are going to complement. Okay, in 1's complement. In 1's complement, the remaining magnitude bits you are going to complement it one by one. So that will be what? 0, 1, 0, 1, 0. So this is what? This is the representation of minus 21 in 1's complement. Now if I want to do it in 2's complement, so that will be what? Whatever is the result we get in 1's complement, simply we need to add 1 to it. So add 1, so this will be 1. So this is 1, 1, 0, 1, 0, 1. Okay, so this is your sign bit and remaining all are your magnitude bits. So tell me, have you understood this, how to calculate your magnitude, sign magnitude representation, 1's complement and 2's complement? Yes or no? Have we understood this or not? Any doubts, any place? Yes. Sir, for positive numbers, what happened? No change. Yes, for positive number, there is no change in 1's complement or even in 2's complement representation. Okay. And one more thing, the first bit in any of the SMR sign magnitude representation, the leftmost bit in your sign magnitude representation, 1's complement and 2's complement, you never actually get what? Means you are never Means all these are what? These are sign bits. Okay, for positive number, no change. Any specific reason for that? Yes, obviously. Because when you do a positive number, like if you do plus 21 plus minus 21, the result you will get is 0. So due to that, your positive number representation, it will not change. Okay, it will not change. It will not change. So you can do that. Add this to, add this to. So this is what? 0 1 0 1 0 1, and this is 1 0 1 0 1 1. So add, so this will be 0 carry 1 0 carry 1 0 carry 1 0 carry 1 0 carry 1. So this will be 0, carry is generated. And further we are going to see whenever carry is generated, so this is a positive number. Okay, carry generated, this is a positive number, and you can see this number comes out to be 0. So whenever basically for positive numbers, the representation, it remains the same, due to the fact that whenever we have to add a positive number and its equivalent negative number, the result should be 0. Now if we change over here, so what will happen? We will be getting a different number in different representation. So that is why for positive numbers, we never change the numbers. Okay, is that okay, everyone? Yeah, so that's okay. So nobody, let me check, because there is no one today, so I had to check actually if someone is waiting or not. Yeah, so let me ask you now, I have given you a 2's complement number. Tell me the number in decimal. What is this number? What is the number in decimal? Quickly tell me. So this is a 2's complement number. So what is the original number? Tell me. So we are going to solve lot of questions in today's session. Okay. So what is the number in your decimal? So nobody is able to answer. Why? Minus 21. Oh, have I taken the same number or what? Okay, so I have taken a same number. Okay, fine. So I have taken the same number. So it's okay. So, okay, let us solve this one only first, then I will tell you. So look, the number over here is what? It is 101011. So I told you by default, in sign magnitude representation, in 1's complement, even in 2's complement, the leftmost bit is sign bit. Okay, sign bit. So if leftmost bit is sign bit, then you can see what? This is 1 over here. 1 corresponds to a negative number. So if you want to get the original number, so what are you going to do? You are going to take 2's complement of the given 2's complement number. Number given. Okay. So you need to do what? You need to take the 2's complement of the given number. So how are you going to do that? So first, keep this sign bit intact. Sign bit should not be disturbed, and bit by bit the remaining terms should be done what? It should be your, means what we should do, we should complement all the magnitude bits. So this will be 1 0 1 0 0, and then we need to do what? We need to add 1 over here because I need to calculate the 2's complement. So this will be what? 1 0 1 0 1, and still this is 1 over here. So you can see this is what this corresponds to 21, and this is your sign bit, so this is minus 21. Okay, minus 21. Now suppose one more example, let me ask you. I don't know what is happening. Computer is getting stuck. So 0 1 0 1 0 0 0 1. Okay. So what is this number? So this number is represented in 2's complement. In 2's complement. So what is the original number? Same. Why will it be same? So you can see I told you what this number is in 2's complement. Okay, this number is in 2's complement. So if it is in 2's complement, so the first bit, this is what? This is your sign bit, and here it is 0. So 0 corresponds to your positive number. Okay, so if you want to calculate for positive number, I have told you that for positive number, your sign magnitude representation, your 1's complement and your 2's complement number, it is the same. So this is what? This is over 0 1 2 3 4 5 6. So 2 to the power 6 plus 2 to the power 4 plus 2 to the power 0. Okay, so whatever is this number. So what happened means, just a minute. Okay, so why was I logged out of my meeting? Just a minute. Okay, so I was using my mobile phone also for this meeting. So there was some issue actually, means two people were actually exited out of this. Yeah. Okay. So this is what? 64 plus 16 plus 1. Okay. So this will be what? This will be your 81. Okay. 81. So what you guys were getting? What you people were getting? You were getting what? 71, I heard someone said. 41, 175. Why? Why such weird numbers are we getting? Huh? Okay, one more, chalo. So we have a number in 1's complement. Let it be 1 0 1 0 1. Okay. So tell me what is the number in decimal counterpart? Okay. What is the number in decimal counterpart? Very quickly tell me. Original number. Okay. So look over here. This number I told you what? It is in 1's complement. So again, look at the leftmost bit, it is 1. So 1 corresponds to a negative number. So if this is negative number, for getting the original number, you need to do what? 1's complement of the 1's complement number given. Then you will get the what? You will get your original number. So if I do 1's complement once again, so keep the sign bit intact, and this will be what? Bit by bit. Rest all the magnitude bit you need to complement. So this will be 0 1 0 1. So this is what? This is your 4. So minus 5 minus, again, why are you guys getting 10? I am not getting. You shouldn't be considering this sign magnitude, means this sign bit, while calculating your magnitude. This shouldn't be taken into consideration for calculating your magnitude. Okay, is that understood? How are you guys getting minus 10? I am not able to understand that. How are you guys getting minus 10? Sorry. So I haven't, means what have I done? So very sorry. So I was only seeing. So I haven't complemented. So 0, oh sorry, 1 0 1 0. Yes, obviously. So I made a mistake. Okay. So I need to complement the given number. So you guys could have told. It's okay. So this is what? This is your minus 10. Okay. I am very sorry. So I forgot to complement the number. So you can see what? This is in 1's complement. Now if the same number was given in 2's complement, so what you would have done? So you already have the 1's complement. So keep the sign bit intact, and the remaining bits you need to add 1. So this will be 1 1 0 1. And this is your sign bit. So this is what? This is your 11. Okay. Minus 11. Is this clear? Tell me. Have to take 2's complement in the previous question. Okay, so I forgot to no, this is your positive number. So positive number, in positive number you don't need to take 2's complement once again. So this is what I am trying to explain. Only for negative numbers only you need to take what? You need to take complement once again. So if your sign bit is 1, then only you need to take. If your sign bit is 0, then for positive numbers, sign magnitude representation, 1's complement, 2's complement, it remains the same. Okay. Okay. So now I have given you few numbers in 1's complement representation. Quickly write down what are the numbers. Okay. Write down what are the numbers. Then I need to make one conclusion. Okay. How do we know given 1 on left side is negative? Sometimes 0 is not given. No. So by default, if it is said the given number is in complemented form, the given number is in complemented, like 1's complement or 2's complement, or simply even if they have written the given number is in complemented form, so by default the leftmost bit, it is your sign bit. Always. Okay. So if the numbers are given in your complemented form, okay, or in sign magnitude representation, always the leftmost bit, it will be what? It will be your negative. So okay. So what is the question over here? It is given 1's complement representation of certain number given, find the number. Okay, so these are all 1's complement number. Now if you write this in your normal decimal number, means in binary, if you convert all the binary to decimal, so this will be 0 1 2 3 4 5 6 7. Okay, in normal binary number. But I have told you what? That these are your complemented, in which form? 1's complemented form representation. So in complemented representation, the leftmost bit are your sign bit. So up to this point, you can see what all the sign bit, they are your 0. So 0 corresponds to positive number. So for getting the original number, I don't need to take complement anytime. Okay. So this will be what 0 means. This is +1. 1 means, sorry, 0 means +0. 1 means +1. 1 means +2. 1 means +3. Now look, in the next 4 cases, your sign bit is what? It is your 1. So if this is 1, that means what? All this number in your ones complement form, they are your negative number. So if these are your negative number, I need to take what? I need to take complement once again. So this will be 1, 1, 1. If I take ones complement of this number, so this will be 1, 1, 0. See, I am not taking complement of the sign bit anytime, only of the magnitude bits I am taking. This will be what? This will be 1, 0, 1, and this will be 1, 0, 0. Now this corresponds to what? This corresponds to -3 because this is your magnitude bits. This corresponds to what? -2. This corresponds to what? This corresponds to -1, and this corresponds to 0, or specifically saying -0. Okay. Okay. So tell me, any doubts up to this point? Any doubts, anyone? Okay, fine. So now look how many bits of number I have used over here. So basically I have used what? 3 bit. And what is the range of number I have represented using this 3 bit? So with the help of 3 bits, I have represented numbers from -3 to +3. Now if this was 4 bit, I could have represented numbers from -7 to +7. How? From 0, 0, 0, 0 to 1, 1, 1, 1. Okay, I could have represented from -7 to +7. Now if I want to generalize this in n bit, so for n bit, the range of number that I can represent using ones complement representation, so that is what? -2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So this is plus. Okay. So usually students get confused. So whenever you get confused, you can do what? You can draw either for 3 bit or for 2 bit, and you can verify the formula, because we are going to see in 2's complement representation, this formula also remains the same. There is just a little bit of changes. Okay, there is a little bit of change. One more thing to note over here is that in one's complement representation, we have different representation for +0 and -0. Okay, we have different representation for +0 and -0. So now for the same thing, let us see in 2's complement. So very quickly calculate. These are the number they are given in 2's complement representation. What number do they represent? What number is being represented over here? So remember, the leftmost bit are still your sign bit. In any kind of sign magnitude representation form, or one's complement, 2's complement representation, the leftmost bit is your sign bit always. So don't forget that. So here you can see this is your sign bit. So for the first 4 cases, as the sign bit is 0, 0, 0, so these are all positive numbers. So this will be plus 0, this will be plus 1, this will be plus 2, and this is plus 3. In the next 4 bits, okay, in the next 4 sequences, you can see what I have a sign bit that is 1. So 1 corresponds to your negative number. So I need to, for getting the original number, I need to take the 2's complement of the given 2's complement number. So if I take 2's complement, what will be the number? So this you can see, this will be 1 0, sorry, this will be 1 0 0. So this I would like to place a star mark over here, okay, at the moment. So I know what is this. So I am going to show you. So this will be 1 0 0. This will be, if I take 2's complement of this number once again, so this is what, 1 0 1 in 2's complement. So take first, keep the sign bit intact, take 1's complement, so this will be 1 0. Now add 1 to it, so this will be 1 1 1. So simply put 1 1 1. Now in the next one I am going to directly put 1 1 0, and this will be what? This will be 1 0 1. So this corresponds to what? This corresponds to, okay, so at this moment let this be star mark, and this will be what? This will be minus 3, this will be minus 2, and this is minus 1. Okay, so what is this? What is this number? What should I write over here? Suppose I ask you, this number is given in your 2's complement form. Okay, 2's complement form. What is the original number? What is the original number? What is the original number? This is also in 2's complement form. What is the original number? So you might be thinking that this is 1. So obviously this is negative number. So if it is a negative number, for getting the original number, I need to take what? I need to take complement once again. So if I take complement, so this will be 1 1 1, and this is 1's complement, so I need to add 1. So this will be 0. This will be 0, means carry 1. So this will be 0, carry is 1. So obviously you might be thinking that over here I will be putting 1 and 0, and over here I get 1, and you will be telling what? Sir, this is your positive number. Okay, this is your positive number. But what is this? This is your negative number. So the result we are getting, that is wrong. Okay, result we are getting, that is wrong, because carry generated, I told you previously, whenever carry is generated, it indicates that you get what? You get a positive result. So carry generated over here, so this result is false. This is a special case of 2's complement. Whenever you have such kind of number in 2's complement, simply you are going to write minus 2 to the power the number of zeros. So this is 1 2 3, so this is minus 8. What about here? So this is minus 2, number of zeros 1 2 3 4, so this is 2 to the power minus 4, sorry, minus 2 to the power 4, so this is minus 16. So over here you can see there are number of zeros is what? It is 1 2, so this will be minus 2 to the power 2, or simply this is minus 4. So this is a special case of 2's complement. Whenever you have such kind of numbers, you simply need to count the number of zeros. Okay, any doubt over here? Any doubt? So what is the range of number that you are able to represent using this using this 2's complement number? So I don't get this notification when someone joins. Okay, so I need to let them in. Yeah, so tell me, What is the range of number that I am representing over here? I am representing the number from -4 to +3. Okay, -4 to +3. So similarly, if I want to represent number using n bit, so that will be what? That will be, yes, very good, Surjit. So that is -2 to the power n minus 1 2 plus 2 to the power n minus 1 minus 1. Okay, so this is the range of number that is generated using 2's complement representation. So this is asked a lot of times. Okay, this is asked a lot of times in such kind of exams. Okay, so now these are your questions. We are going to solve them one by one. So very quickly tell me what will be your answer over here. So what will be your answer? Okay, so B. Okay, so look, what is the given number? The 2's complement of a number given is 1010101. Okay, so this is a 2's complement number. So we know what in 2's complement number, the leftmost bit is your sign bit. So this is 1. 1 corresponds to negative. And if we want to get the original number, what I need to do? I need to take the complement of the given 2's complement number. So that will be what? 1 1 0 1 0 1 0. Add 1 over here. So this will be 1. So 1 1 0 1 0 1 1. Okay. So the 2's complement of the number. What does this mean? Why have they taken 1 over here? So this is a 2's complement of the number of 101 is. Okay. Why have they complemented the sign bit over here? Sign bit shouldn't be complemented. So this is, why is the sign bit complemented in this question? So that is what. Yeah, so this is one thing that we are getting. So sign bit shouldn't have been complemented over here. It should remain like this only, 1. Okay, so this was a mistake in this question. Sign bit shouldn't be complemented. Okay, it should be the way it is. So the remaining terms we are getting same. So option B is correct. Only thing being, maybe not signed number. They wanted us to simply find the 2's complement. Yeah, even that could have been done. Means they are simply, without considering the sign, they are just asking us to find the 2's complement of the sequence. Okay, 2's complement of the sequence. That also they would have asked. So yes, that would have been also the answer. Means they have considered this. Okay, so they would have like done like this. So it's okay. Still, sign bit shouldn't be, never ever complemented. Okay. Okay. So now we have this. Tell me now. For this, what is your answer? Confused, sir? What confusion you have? Tell me. Where confused? See, I am telling sign bit should never be complemented. Okay, sign bit should never be complemented. So this type of confusion even I had when I was doing. So somewhere you will see that what is happening, they are not complementing the sign bit. Somewhere you will see it is getting complemented. So always remember, never do this. You should never mess around with this last, means this leftmost bit. Okay, leftmost bit, you should never ever change it, because that is your sign bit. Now if you change it over here, you can see they might not be asking. Okay, they might not be asking what is the value of this number. They are simply asking what is the 2's complement number of this sequence. Okay, what is the 2's complement of the sequence, simply they are asking. That is what they are meaning over here. Okay, so if you just simply want to calculate 2's complement, so that is what, first you need to calculate 1's complement of this number. So 1's complement means what, bit by bit you need to complement. So that will be 0 1 0 1 0 1 0, and then you need to add 1 to it. So this is 1 1 0 1 0 1 0. So you can see you are getting this number, but this is actually wrong. Okay, you should never complement the sign bit. Okay, understood? Srihari, others can solve this problem. Srihari, let me know if you have some doubt. Okay, 7-bit minimum. Okay. So now we need to represent from -50 to +50. Okay, so for representing 50, how many numbers do I require? Representing 50. So that will be, so this is what, 1 1 0 0 1 0. Okay, 50 this is. So how many bits do we require? 1, 2, 3, 4, 5, 6. Okay, 6 bits is used for representing of -50. Okay, sorry, for representing 50. This is used for representation of 50. Okay, this is 50. Now I need to represent from -50 to +50. Okay, -50 to +50. So if you take like 6-bit, okay, here you have 6-bit. So where will you place these sign bits? You cannot do that. So you need one more bit for your sign bit. Okay, you need one more bit for your sign bit. It can be, this is +50. If you want to represent -50, this will be 1 1 0 0 1 0. So 7-bit. So at least you need how many bits? You need 7 bits. So option A is your correct answer. Okay, correct answer. Now this one, tell me. This is a good question. Option D. Anyone else? Option D. Very good. So option D is your, what is it? 1, 2, and 3. So which of the following notations have two representation of zeros? So always remember, two representation will be present in your odd complements. Okay, in your odd complements it will be present. So you can see ones complement with the radix of number 2 being 2. So this option we have already seen. Now whenever seventh complement, so here basically your radix of the number being seventh complement with radix of number being 8. So that means what? This is your, this has representation from 0 to 7, and means here what we had from 0 to 1 means this is what? Radix is 2. So that means we have two characters 0, 1. Nines complement with radix of the number being 10. So this will be what? From 0 to 9 we have number. And here tens complement with radix of the number being 10. So this is also 0 to 9. So whenever we have odd complements at that positions, we are going to have what? We are going to have your basically two representation for your zeros. So obviously this is ones, this is sevens, this is nines. So these are all odd representation. So obviously option D is your correct answer. Okay, option D is your correct answer. Okay, so now this question. This question, C, B, someone is getting C, someone is getting B. Again, change Sankari. Sir, number of bits are different. So assume 0 on left. No, no, no. You won't be assuming zeros on left. Why are you going to assume zeros on left? So what is given in the question? These are your numbers, okay? 1, 2, and 3 correspond to 2's complement representation. So now if you think that this is 5 bit, this is 4 bit, and this is how many? 6 bit. So I need to equalize the number of bits. So we will add two zeros over here. So this will then give you wrong result. Why? Because if you add zeros, you can see this is in 2's complement. So the first bit corresponds to your sign bit. So this is negative number. But if you add two more zeros over here, so what will happen? This won't be your sign bit anymore. Your sign bit will be this then. So then this will correspond to your positive number. So never ever change your number of bits in sign magnitude representation. Okay. And even if you suppose, okay, so I should have told you this. Let me see. So before solving this question, let us solve this using 2's complement. Okay, very quickly. So why this doubt? Let me clear it for once and all. Okay, once for all, let us clear this. So look very carefully. If I want to solve this using 2's complement, so 9, it will be represented as how? It will be represented as 1, 0, 0, 1. So this is what? This is your decimal equivalent. If I want to represent it in sign magnitude representation, what happened? Yeah. Sign magnitude representation of +9. So this will be what? This will be 0, 1, 0, 0, 1. Now I told you for positive number, sign magnitude 1's complement, 2's complement, it will remain the same. So even 2's complement for +9, it will be what? It will be 0, 1, 0, 0, 1. Okay. Now for 26. Okay. 26. So 26 is what? 26 is equal to your 16 plus 8 plus 2. So this will be 1 0 1 0 1. Is this correct? No, this is not correct. Okay, so this is your 26. Now if I want to represent sign magnitude representation of minus 26, so this will be what? This will be 1. This is your sign bit, which corresponds that this 26 is negative, and this remaining bit, so this will be what? 1 0 1 0 1. Now if I want to calculate the 2's complement of this number, simply what I need to do, I need to take complement once again, 2's complement once again. So this will be what? 1 0 0 1 0 1, and I need to add 1 over here. So this is what? 0 1 1. So 0 1 1 0 0 1. So this number is what? This is your minus 26 in 2's complement. So now what I will be doing? I will be adding this two number. So minus 26 is what? It is 1 0 0 double 1 0. So this is minus 26, and over here what I have plus 9. So plus 9 is 1 0 0 1. So now you can see there is bit mismatch. So what am I going to do? Whenever there is bit mismatch, remember to copy the sign bit. Okay, don't put zeros. You need to copy the sign bits over here. So sign bit, so this I have represented, means, or this one, okay, plus 9 I had to represent. So sign bit over here is 0. So you need to copy this further. Okay, you need to copy this further. So now do the calculations. This will be 1 1 1, and this comes out to be 1 0 1. So now look, the result I am getting, what is the sign bit over here? It is again 1. So if this is 1 in 2's complement, while I had performed the arithmetic in 2's complement, so once again when I am getting 1 in your leftmost bit, and this number when I have solved, there is no carry generated. Whenever no carry generated, it implies basically the number that I have got is negative. So if I want to get the original number back, what I need to do, I need to take 1's complement once again. So this will be 1 1 0 0 0 0. Now this is 1's complement. Add 1 one more time. So this will be 1 0 0 0 1 1. So this number is what? This is 16 plus 1, 17, and this is minus, so this is minus. You can see minus 26 plus 9, it comes out to be minus 17. So this is what I am getting. So never ever copy anything in front of your this number, complemented number. And even if you want to copy, you need to copy what? You need to copy the sign bits. Okay, so over here if you see these numbers, so these are different numbers, and they are represented in 2's complement. So did you understand what will be the problem if you assume 0 to the left? Srihari, did you understand? Did you understand? Okay, fine. So now let us calculate this. So if we calculate, so here you can see the leftmost bit is what? It is 1. So this is a negative number. So if this is negative number, so the 2's complement will be what? So this will be 1 0 1 1 0. Now add 1 to this. So obviously this will be what? This will be 1 1 1 0 1. What is this? So this is your sign bit. I have kept it intact, and this corresponds to what? This corresponds to your 7. So this will be minus 7. Minus 7. So now I will be telling you one shortcut trick to calculate 2's complement. Means how much longer we can do like this. Okay. So shortcut trick is, look very carefully. Again you can see the leftmost bit is what? It is 1. So 1 corresponds to a negative number. Okay, negative number. So whenever we have negative number, we need to take 2's complement once again. So what is the shortcut trick for calculating 2's complement? Start from the leftmost bit and check where you get the first one. Just copy it down. The remaining magnitude bit you need to complement. So complement this. This will be 1 1, and this is sign bit. I keep it always intact. So this, the 2's complement will be what? It will be 1 1 1 1. So again this corresponds to -7. Now let us check for this. So again you can see this is negative number. So negative number means what? I need to take 2's complement once again. So shortcut trick is what? From the leftmost bit, search for the first one. You get it over here. So this is 1. And remaining bits you need to complement. So this will be 1 1 0 0, and this is 1. So this again you can see is what? This is -7. Okay, this is again -7. So option C is correct. Basically what they have done, see, if you want to represent -7, it looks something like this in 2's complement. So what I told, if you copy the sign bit in your left side, the number will remain the same. So here you can see they have copied the sign bit twice like this. So where is the number? Yes, so this will be 0 0 1. So this number you can see they have copied the sign bit twice, and over here the sign bit copied is just once. Okay, so these are what? These are means they have copied the sign bit. Any doubts up to this point? Okay, fine. So now let us see what? Conversion of number system. So this is very simple. Okay, very simple. We all know. So I am not going to spend, sir, how to check overflow occurring or not in sign magnitude. Yes, we are going to see. We have that topic also. We are going to see that also. No need to worry. So decimal to binary. Okay, decimal to binary. First, let us see how to do this. So this is very simple. Suppose I have a decimal number 10. So how do we calculate? So we keep on dividing it with 2. So this will be what? 2 5. Remainder is what? Sorry, remainder is 0. So again divide it with 2. So remainder is 1. Again divide it with 2. So this is 0. So now you need to write from your below point. So write all the remainders. So this is what? 1 0 1 0. So this point is your MSB, and this point is your LSB. Very simple. Okay, suppose if you want to write 0.750, so what will be the corresponding binary representation of this decimal number? So simply you need to multiply it with 2. So this will be what? 1.500. So this number you need to take, and remaining this one you bring once again and multiply it with 2, and this comes out to be what? 1.000. Now you cannot continue the multiplication more because it is terminated with 0 0 0. So 0.750 in your binary representation, you need to move from top to down. So this will be your 0.11. So this will be your MSB, and this will correspond to your LSB. Okay, so if you want to write 10.750, it will look something like this: 1010.11. Okay, so these are very simple things. Just for once, for revision purpose, I have done. Now similarly for binary to decimal, like if we have in binary, how do we convert it to decimal? So beyond this point, okay, what we do, we add it to the powers of 2. So this will be 0 1 2 3. These are all positive power, and to the right we have your negative power. So this will be -1 -2. So this is what? 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0, plus over here this will be 1 into 2 to the power -1 plus 1 into 2 to the power -2. So this is 10, and over here this will be what? 1 by 2 plus 1 by 4. So this is 3 by 4. So this will be 10 3 by 4, or you can even write 310.75. So the same number we had done previously also, 10.750. Okay, so we are getting 10.75. So now how to convert binary to octal and octal to binary? Suppose octal means what? Now I am not defining over here that what is octal representation. Okay, so octal representation, basically we have characters from 0 to 7. Okay, so this is what octal representation. Like a number 72. Okay, this is a valid octal number. But 93, is this a valid octal number? No. Why? Because octal representation, you have numbers from 0 to 7. So how will 9 come over here? So this is wrong. So how to represent binary to octal or octal to binary? Okay, very simple. Suppose if I have a octal number 72. Okay, this is your octal number in 72. So simply you are going to write the 3-bit binary number of this 7 and 2. So 7 can be represented as 111 and 2 can be represented as 010. So this is your means octal to binary representation. Now suppose if I have a binary number something like this. Okay, binary number something like this. Now I want to convert it to octal. So starting from the leftmost bit, make a group of 3. Group of 3. So this is first group of 3. This is another group of 3. This is another group of 3. So this number corresponds to 4. This corresponds to 2. And this corresponds to 5. So the octal equivalent of this binary number is what? 524. Now suppose if the number was something like this. Okay, something like this. So again, let us start making the groups from your leftmost bit. So this is first group of 3. Then you can see I cannot make group of 3 anymore because there are only 2 bits over here. So you need to do what? You need to pad it with zeros. So pad it with 0. So if you pad it with 0, so this is what? This corresponds to 4 and this corresponds to 2. So this whole number, it corresponds to 2 4 in your octal representation. Any doubts with this? Any doubts, anyone? Okay, fine. So now let us move forward. Next is what? Hexadecimal to binary and binary to hexadecimal. So in hexadecimal, we have from 0 to 15. 7, 8, 9, 10, 11, 12, 13, 14, 15. So 0 is represented with 0. Up till this point, we have no problem. But how do we represent 10 in hexadecimal? We give it A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. Okay, so where is hexadecimal numbers prominently used? So this can be asked to you people. Where is hexadecimal prominently used? One place where you use hexadecimal numbers frequently? Yes, very good. In microprocessor. Okay, in microprocessor, we usually use hexadecimal numbers. Okay, so now look very carefully. Suppose if I want to convert to F. So this is what? This is your valid hexadecimal number. Okay, if I want to convert this into binary, so how will I do? So write the 4-bit equivalent of this individual character. So F is what? 15. So if I write it in 4-bit binary, so this will be 1 1 1 1, and 2 I can write it as 0 1 0 0. Okay, so now if I want to write the binary equivalent of this hexadecimal number, so this will be what? 0 0 1 0. 1 1 1 1. Now same thing, if I have a binary string like something like this 0 0 1 0 1 1 1 1 0 0. So how do I convert it to hexadecimal? So starting from the leftmost bit, make group of 4. So this is one group of 4. This is another group of 4. Let me assume there was one over here. So you can see that there is one missing over here, one bit. So I can zero pad it simply. So now write the corresponding numbers. So this is what? This is your 10. So 10 corresponds to A. This corresponds to what? 8 and 2, 11. So this will correspond to B. And this is your 4. So 4B A. This is in your hexadecimal number. Okay. Any doubts in this? Sorry, this is 12, na? So 12 corresponds to C, 4BC. Okay, 4BC. Fine. Now, quickly tell me what will be the result over here. What will be the result over here? So this is a good question. This is very simple. Look, what is the addition of minus 64? This is given in decimal. 80 in hexadecimal. Now, if you either you can do what? You can convert this number to your decimal number and solve. Okay. So very quickly, if I want to convert this to decimal, what I can do? So take out the binary equivalent of this number. So that will be 100 and this will be 000. So this you can see what? 0 1 2 3 4 5 6 7. So this is 2 to the power 7. So that is 128 in decimal. So minus 64 plus 128. So that will be 64 plus 64. Now look, where is plus 64? So this is in hexadecimal. This is wrong. This is also not 64. Directly you can see this might be 64. So this is 0 1 2 3 4 5 6. Yes, 2 to the power 6. So this is 64. Okay. So very simple. Like this you can solve. Now for this one, tell me very quickly what will be the answer. Yes, tell me, Srihari, what doubt you have? Last question. Others can solve this. So copy down the question. Yes, tell me what is your doubt, Srihari? 64 in binary. Yes. So 64 in binary is written like this. So what is the doubt? How option D? So this is what? 0 into 2 to the power 0 plus 0 into 2 to the power 1. Like this till 0 into 2 to the power 5 plus 1 into 2 to the power 6. So 2 to the power 6 is what? It is 64. And as this is a positive number, so sign bit will be what? It will be 0. So option D. Yeah. So what is the answer you are getting for this one? See, look very carefully. Given 135 in base x, 144 in base x, and 323 in base x, what is the value of base x? Okay. Suppose if I give you a number like this. So we know what this is your units place. This is a decimal number. This is tens place. This is hundred place. So how do we write the number? 1 into 10 square, 100 place. This is what? Tens place. So this will be 0 into 10 to the power 1. You can see tens place. And this is what? This is units place. So this is 1 into 10 to the power 0. If you add this, this will be what? 100 plus 0 plus 1. So you are getting 101. Same for base x also. Here your base was 10. Here your base is x. So if I want to write this number in this format like this, so this will be what? You can see this will be x square, 1 into x square plus 3 into x to the power 1 plus 5 into x to the power 0. This number, this will be what? 1 into x square plus 4 into x to the power 1 plus 4 into x to the power 0 is equal to 3 into x square plus 2 into x to the power 1 plus 3 into x to the power 0. So if you solve this, this is x square. So this will be what? X square. And over here, this is 3, 7. So this is 2. So this will be minus 5x. This is 5, 4, 9. And this is plus 3. So this will be minus 6 is equal to 0. So what is the value you get? X minus 6, x plus 1. So x can be equal to 6 or it can be equal to 1. So minus 1. So radix cannot be negative. So what is the correct answer then? It is 6. So 6 is the correct answer. And even you can see that you have characters like 1, 3, 5. There is no number over here that is more than 6 over here. Okay. More or even equal to 6. So for base 6, you will have digits from 0, 1, 2, 3, 4 and 5. So only these digits are present over here also. Okay. Sorry, 6, 2 or 3. Array, middle term splitting. How will it be 2 or 3? So for this question, tell me very quickly. So this was gate question, yet I have taken because this question can also be solved, okay, in your PSU question. So complements arithmetic already I have done with you guys. So solve this very quickly. Very quick answer give me. What? XY is equal to 30. What, have I done some mistake or what? XY is equal to 30. I am getting something else. So 1 into 5 square, 2 into 5 and 3 into 5, 0. So this is 3. Oh yes, 33 I have taken. See. So that was for 5. Okay. Yes. So this is 38. So xy is equal to 30. Okay, fine. Yeah, Sankari. Okay, so xy I am getting as 30. Now what can be the combination of x and y so that I get 30? So 8 possible you guys are telling. Possible solution is 8. So anyone else have any answer? So 8. Okay, Surajit is telling 8. So the possible combinations can be x can be 1, y can be 30, x can be 2, y can be 15, x can be 3, y can be 10, x cannot be 4, it can be 5, so this can be 6, so this can be 6, this can be 5, 7, 8, 9, 10. Once again, if x is 10, this will be 3, 11, 12, 13, 14, 15. If this is 15, this will be 2, and last is what? If this is 30, this will be 1. Now check very carefully. If y is 30, okay, if y is 30, then x is 1. So y is what? Y is your radix, or it is your base. So when base is 30, so you can have your units from 0 to 29. Now 29 can be represented with any alphabet or anything. So this case can be possible. Look over here. If base is 15, so you can have numbers from 0 to 14. So x can be 2. This is also possible. Okay. So look at this. Y can be anything that has what? That has from 0 to 8. Okay, 0 to 8 character, because the highest digit over here is 8. Okay, the highest digit is 8. So base, if it is greater than 9, okay, if base this y is greater than 9, then what will happen? I will be getting a satisfactory result. So base greater than 9 is in how many places? Over here, here. So only 3 cases are there. Okay, only 3 cases are there where base is greater than 9. But how are you guys getting 8 possible solution? Why 8? Why 8? 3 possible solutions you are getting. Okay, so not 8, 3 is the correct answer over here. Okay, Sri Hari is getting 3. Surjit, did you understand what is the mistake? These 1, 2, 3, 4, 5, 6, 7, 8. So you have calculated all this. So these are invalid. By trapping in question. What trapping? You got trapped. Okay. Okay, so don't get trapped. Okay, so these are invalid. Why? Because if your base is 6, that means y is 6. So for 6, you will have digits from 0, 1, 2, 3, 4, 5. Okay, but here you can see that in the units place you have 8. So that is an invalid digit in a base 6 system. Okay, so that is wrong. So your answer will be what? It will be 3. Now complements arithmetic. Okay, complements arithmetic, how to solve already I have discussed, but still let me show you one more time. So minus 26 plus 9. If I want to do this, okay, let us this time do first plus 26 minus 9, and then very quickly we are going to do minus 26 plus 9. Okay, or even we can do some other numbers also, but this is okay. So 26 is what? It is 1 0 0 1 0. Okay, so this is 26, and 9 is what? 9 is 1 0 0 1. In the first case, look, 26 is positive. So what is the sign magnitude representation of 26? It is 0. 0 is your sign bit, and magnitude is what? 1 0 1 0. So for positive number, we know what? One's complement is same as your sign bit. So this will be 0 1 1 0 1 0. Okay. Now come to 9. So 9 in sign magnitude representation, it will be what? plus 9, if I have to talk about plus 9, so this will be 0 1 0 0 1. But here what I have, minus 9. So for minus 9, your ones complement is also different. So that will be what? You need to change the sign bit and complement all of this one by one, bit by bit. So this will be 0 1 1 0. So this is minus 9 in your, sorry, first I should have written in sign magnitude representation. I am very sorry. So this will be 1 0 0 1 in sign magnitude representation. Now if I want to write minus 9 in ones complement, so that will be what? Sign bit will be intact as your sign magnitude representation, and the magnitude bits you are going to complement it bit by bit. So this will be 0 1 1 0. So this is your minus 9, this is your plus 26. So now add this two. So always write it from the leftmost bit. So this is 0 1 1 0 and this is 1. So you can see you are short of one bit. So just copy the sign bit over here. So this is 1. Now add this 2. So this will be 0. 1 plus 1 is 0. 1 over here. So this is 0. Carry is 1. Again 0. This will be 1. 1 plus 1 0. 0 plus 1 1. Carry is over 1. So 1 plus 1, this is 0. Carry is 1 over here. Okay. Carry is 1 over here. Okay. So carry generated means what? Carry generated means your positive number. It indicates a positive number. But in ones complement, remember this. Whenever in ones complement, if you get a carry while doing your arithmetic process, you need to add this. Okay. So add this over here. So what you will get? 1 0 0 0 1 0. So now solve this. This is what? This is 16 and 1. And over here this is 0. So this is plus 17. And we know what? For this we get plus 17. So whenever carry is generated, it indicates a positive number. Carry not generated, it indicates a negative number. And in ones complement, whenever carry is generated, it is added to your least significant bit of the result to get our answer. Tell me, is this process clear to everyone? Is this process clear? Okay, so now let us solve minus 26 plus 9. Okay, minus 26 plus 9. So I will solve it over here. So plus 9 in sign magnitude representation, it will be 0 1 0 0 1. 26 in sign magnitude representation minus 26, it will be represented as 1 1 1 0 1 0. Now if I want to represent ones complement of minus 26, so sign bit keep it intact, remaining all the magnitude bits you need to complement it one by one. So 0 0 1 0 1. So this is your minus 26 in ones complement. Now we need to add this one, and okay, so ones complement means of 9 plus 9, it will remain the same. So I forgot to write that. So plus 9 in ones complement, so that will be 0 1 1 1 0. So this is what? 1 0 0 1 0 1, and add this. So 1 0 0 1 0. So again there is a bit mismatch, so you can copy the sign bit. So this is what? 1 plus 1 0. Carry 1 1 1 0 1. See, no carry is generated. No carry generated means negative number. And over here also you can see that the sign bit is what? Sign bit is 1. So that means this indicates a negative number. And if this is a negative number, for getting your result, you need to take ones complement once again. So this is 1, sign bit copied, and take ones complement. So this will be 1 0 0 0 1. So this is what? This is your minus 17. Okay, so minus 17 you are getting this time. Did we understand this or not? So already for 2's complement I have solved previously, so I am not going to show this to you. Now let us understand the concept of overflow. What is overflow? So what I want you to do, solve this 4 operations minus 3 plus 2, okay, minus 2 plus 3, then 2 plus 3, and minus 2 minus 3. Solve this very quickly. Okay, solve this very quickly. So I am also going to solve. You guys also solve. Using 2's complement. Okay, solve it using 2's complement. Oh, so I have done one mistake. Okay, is this clear? Are we getting something? Where will overflow occur? So what is this overflow? Let us understand very quickly. Okay. So look very carefully. First is what? Minus 3 plus 2. So one by one, let us solve. Okay. Minus 3 plus 2. So minus 3 corresponds to what? I have already solved 2's complement. So that is 101. And plus 2 is what? It is same as your 2's complement, means sign magnitude representation will be same as your 2's complement. So that will be 0, 1, 0. So solve this. This will be what? 1, 1, 1. Okay. No carry generated. Okay. No carry generated. Look here very carefully. No carry generated. So that implies what? This is a negative number. For getting your original number, I need to take 2's complement once again. So this will be what? 1, 1, 0. So this is what? Minus 1. Okay, this is minus 1. Simply I have calculated 2's complement once again of this number. So that is 101, keeping the sign bit intact. Now look very carefully. There are few things that I have to show you. So this point, what is the carry? This is C in, and this point, this is C out. C out is the carry that we get from this one, and C in is the carry we get from solving this 2-bit. Okay. So from here, when I had added 1, 0, it was 1. 0, 1, when I added, it was 1. C in is 0. And 1, 0, when I added, it was 1. And C out is also 0. So in this case, C in is 0. C out is also 0. Okay. Now next come to the second case, that is what? -2 plus 3. Okay, so -2 plus 3. So that will be what? -2 is given by 1 1 0 and plus 3 is given by 0 1 1. Add this 2, so this will be what? 1 1 plus 1, look, 0, carry 1, 1 plus 1, it is what? 0, again carry is over here is 1. So this one, this is C in, and this one, it is your C out, carry out. So look here, carry in is 1, carry out is 1, and we get a positive number over here, that is what? 0 0 1. So if I want to convert it back to decimal number, so this 0 is what? Sign bit, and this will be what? This will be plus 1. Tell me up to this point, is it clear? Quickly tell me if it is clear or not. So what is happening? You guys exit, then again I have to include you. So there is some issue or what? Means I am also not able to see. Okay, so randomly I have to once again go and check. So tell me up to this point, is it clear? You can see that I am calculating these two things. This point I am telling the carry generated over here is C in and this is C out. Okay, so these are valid results I am getting up to this point. Now see, when I add 2 plus 3. So when I add 2 plus 3, so let me use some different color. So plus 2 I have already written, it is what? In 2's complement it will be same as sign magnitude representation. And plus 3 will be what? 0 1 1. Add this 2, so this is 1. 1 plus 1 is 0, carry is 1, so this is 1. Now you can see what? Over here I am getting C out as 0 and C in as 1. You can see one more thing to note over here, that there is no carry being generated. So if no carry generated, I should be getting a positive number, but you can see the number that I get, it is a negative number. Why so? Because the leftmost bit is 1. So this indicates a negative number, but I have not generated any carry. So there is some kind of mistake over here. So it's okay. Let us still write this as C in and this as C out. And if I convert back this number, okay, so this is a negative number. If I calculate the 2's complement, this will be 1 1 1. So that is what? That is -3. Okay, this is -3 in 2's complement. Now the last number is what? -2 -3. So -2 -3. So -2 is what? -2 is 1 1 0 and -3 is 1 0 1. Now look very carefully. Once again, if I add this 2, this will be 1 1. 1 plus 1 is 0. Carry is 1. Okay, so here it was 0 because 1 plus 0 is 1, carry 0, and this is 1 plus 1 0, carry 1. Again you can see there is some problem. Carry is generated. Okay, carry is generated, but here what you can see, that this is a positive number and carry generated means what? It is positive number. But if you look at this number from 2's complement, this is a positive number, and if you want to calculate the original number, this is what? This is plus 3. But we know what? -2 -3 is what? It is -5, and here it will be +5. So that means what? There is some problem in these two cases. So this is known as what? This is known as your overflow. Now why is this overflow occurring? Because we know what? With the help of 3 bits, in your 2's complement, I can represent number from -4 to +3. Okay, with 3 bit I can represent number from -4 to +3. But look over here, what is happening? I am representing number, you are representing number that is +5, -5, So that means what? These are, you can see this result is what? This is a 3's bit 2's complement number. Even this is 3's bit 2 complement number. This is also 3's bit 2's complement number. Now with the 3's bit 2's complement number, the range of number that we can have is from -4 to +3. So here what we got? -1, +1. So this was in this range, -4 to +3. But look over here, when we got the number over here, this is +5. So +5 is out of the range. Even here -5, this is also out of the range. So that means what? Here there is some problem. Okay. The problem is known as overflow. Now how to detect overflow? So look here very carefully. If C in XOR C out is equal to 0, then no overflow. So this I am erasing now, this part. This is not required anymore. If C in plus C out is equal to 0, C in XOR C out is 0, no overflow. But if C in XOR C out is equal to 1, then overflow is happening. Overflow is happening. And one more thing. See, this is one concept of detecting overflow. Another concept of detecting overflow is that, look at these two cases. Okay, at this two cases, this case and this case. When you add two negative number, you cannot get a positive number. And when you add two positive number, you cannot get a negative number. So this is one more concept that you need to know, that overflow, it will happen when, if you add two positive numbers or if you add two negative numbers. Now suppose if you had added -1, result will be -2. So here overflow will not happen. Why? Because this is in the range of 3 bits 2's complement representation, -4 to +3. So -2 lies in the range. So usually whenever you add two positive number or two negative number, there is a chance of overflow. Tell me, someone was asking, sir, when will you talk about overflow? So Surajit was telling. Is that clear now, Surajit? Is that clear? Okay. So now I have a question for you guys. Okay, question. Surajit, was that clear to you? Everybody, is this concept clear? Tell me yes or no. So solve this question and let me know what is the answer you are getting. Means whenever there is a overflow, answer coming always wrong. Can we conclude? Yes. Whenever overflow is occurring, the answer that you get using 1's complement or 2's complement, that is wrong. So if you wanted to get the correct result of this one, -2 plus 2 plus 2 plus 3, if you wanted to get the correct result, so what you needed to do basically, so you should have represented the number +2 something like this. Now this is sign bit, these three are your magnitude bit, and this number is what? 0, 1, 0, sorry, 1, 1. So this is your sign magnitude representation. Now same will be for 2's complement also, because for positive number we know what sign magnitude representation is same as your 2's complement. So if you add now 0, 0, 1, 0, 0, 0, 1, 1, so this will be what? 1, 1 plus 1 is 0, carry is 1. Now you can see this, you are getting 0. Okay, 0. So here you can see what? C out is 0, even C in is 0. So the number you can see, this is C in, This is C out. So C in XOR C out, it will be 0. And even the number you are getting, you can see this is sign bit 0 corresponds to positive number, and this corresponds to 5, which is in the range. Okay, so this is your correct number. When you represent using 4-bit in 2's complement, you are getting the correct result. Okay, so your overflow occurs when you have less number of bits in your 2's complement. So now solve this question very quickly. See what is given. The addition of 4-bit 2's complement binary number, this and this result. So these are 4-bit 2's complement. So look very carefully. 1 1 1 1, and this is 0 0 1 0. So add the numbers. 1 plus 0 is 1. 1 plus 1 is 0. Carry is 1. So again 1 plus 1 is 0. Carry is 1. So this is your scene. 1 plus 1, it will be 0. Carry is 1. So this place is C out. C out. Okay. So if you see C in XOR C out, this is equal to 1 XOR 1. So that is 0. That means no overflow has taken place over here. And the result that you are getting, it is correct. So 0 0 0 1 and no overflow. Is that clear, everyone? Is that clear? Okay, fine. So the next question, solve it very quickly. Yes, C is the correct answer, Surji. Now, what is the answer for this question? So such kind of question you are going to see where your this options, they might look a little bit confusing. So what answer are we getting for this one? B. Okay, look. Positive logic in a logic circuit is one in which logic 0 and logic 1 are represented by 0 and positive voltage are represented by 0 and positive voltage, any positive voltage. Logic 0 and 1 are represented by negative and positive voltage. Okay, so you are telling B. So here it is positive logic. Logic 0 voltage level is higher than logic 1 voltage level. So this is what? This is your logic 0 voltage level is higher than logic. So this is your negative logic. Option D is what? Logic 0 voltage level is lower than logic 1 voltage level. So option D. Now positive logic, I told you what? In positive logic, 0 corresponds to a lower level and 1 corresponds to a higher level. So you can see option A is telling what? Logic 0 and logic 1 are represented by 0 and positive voltages respectively. Now they haven't mentioned this positive voltage, but look here what they have said in option D. Logic 0 voltage level is lower than logic 1 voltage level. This will be true. See, you can take 0 volt over here plus 5 volt over here, or even you can take 1 volt over here, or over here you can take 5 volt. Now it depends on you. So this statement, this is correct, but it is not as correct like this, because this needs to be always hold true. Now logic 0 is represented, I can even represent logic 0 as -5 Why option A is wrong, I am telling. Okay, are represented by 0 and a positive. Okay, so even option A can be correct. Okay, even option A can be correct for positive logic. So I guess this is multiple select type question. So option A and D both can be correct. Okay, both A and D can be correct. Tell me, is this clear? Okay, fine. So next is what? Next we have is logic gates. So logic gates. Okay, so we can quickly just discuss about what is logic gate. So logic gates, we basically have three kinds of logic gates. Okay, so first kind is what? Basic gate. Second is what? Universal gate. And third is what? Special purpose gate. In this basic gate, we have three kinds of gate. So the first one is what? And. Second is what? Or. And last is what? It is your not. In universal gate, there are again three kind of gates. Okay, they are what? NAND first is, second is NOR, and in third kind of special purpose gate, we have two more sub classification. It is what? XOR and XNOR. Okay, XOR and XNOR. So now let us see very quickly in today's session what is basic gate, because it's already 8, so you have one more session from 8:30. So I will leave you people at 8. So what is AND gate? AND gate is represented like this. So if I want to draw the truth table, what is truth table? What is truth table? Truth table is basically the combination of all the inputs and outputs for a logic gate. Okay, for a logic gate or a logic circuit. So your AND gate basically, it has your output high, it has your, this is your output, these are your inputs. So your AND gate, it will have output high when all the gates are, when all the inputs are high. What I said? AND gate has output high when all the inputs are high. So you can see at this place both the inputs are high, so this will be high. If an AND gate has any one of the input low, the output is going to be low. So this is low, this is low, this is low. Why? Because any one of the input you can see over here is low. And if you want to write the logical expression for your AND gate, that is A dot B. Okay, this is A dot B. Now you can represent this using positive logic or your negative logic. It depends on you. Okay, if you represent it using positive logic, so this will look something like this. So in positive logic, low corresponds to 0, high corresponds to 1. And in your, this is your positive logic. In negative logic, 0 corresponds to high and 1 corresponds to low. Okay. So this will be what? Low, low. This will be 1, 1, 1, 0. Okay. So this is in negative logic, the truth table. This is in positive logic, the truth table. Any doubts in this? Okay, fine. So now the next is what? We have OR gate. So OR gate is represented like this. Okay, A, B, X. And here basically the output of OR gate is low when both the inputs are low. Okay, so this is your universal truth table. So this will be low, this will be high, this will be low. Why? Because both the inputs are low. Here you can see any one of the input is high. Here both the inputs are high, so this will be high. If you want to draw the truth table in your positive logic, so it will look like this. Okay, so this will be what? This will be 0, this will be 1, 1, 1. If you want to draw in negative logic, so this will be what? Okay, so this is in your negative logic. Tell me if this is clear or not. Is this clear? Is this clear? Any doubts in this? Any doubts? So this is OR gate. Okay, so the last gate that we have, what? 2 times written. What 2 times written? What 2 times written? What 2 times? This is in positive logic, this is in negative logic. 2 times written negative logic. Where? Okay, so this should have been 0, 0. I'm very sorry. Yes. So this should have been 0, 0. Yes, this should have been 0, 0. Okay. Fine. Okay. So this is positive, this is negative logic. So the last basic gate is what? It is NOT gate. So NOT gate, it is defined like this. Okay. So basically it is what? It is inverted. So whatever is A, opposite will be your output. If A is low, X will be high. If A is high, X will be low. And its logical expression is denoted by A complement. So this is what? This is your NOT gate. Okay. This is your NOT gate. So with this means we end today's session, because propagation delay in gate, this has very good concepts that we need to see. So in the next session, we are going to see what? We are going to see your propagation delay, and we are going to see also Boolean algebra. Okay. So the next session, I guess it will be on Wednesday. Okay, it will be on Wednesday if I am not wrong, according to the schedule. It will be on Wednesday. Okay, so if there is any doubt, you can ask me, or else we will be ending today's session. So from 8:30 you have one more session. Okay, so you kindly attend that session also. It will be helpful for you. Okay, any doubts?